Yes, hello. Let's talk about HPC and FLEUR. HPC in this context is high performance computing. And what do we mean with high performance? Let's compare these two machines. One is a usual laptop. You usually have something like a couple of cores on it and about 8 GB of memory. And this nice machine, which you will see tomorrow, as I understood, in Supercomputer Center. This machine has 45,000 cores and 2,000 terabytes of memory. And if you want to run your program on this kind of machine, you need to program your code in a special way, run it in a special way, and you should understand a bit how this hardware works. But the first question, why bother actually? Well, why do we need this machine, or maybe we are quite happy with laptops? The main reason, the reason is that the time to solution scales cubically with the system size, with the number of atoms. Here in the table we have several examples. What would it take to converge a system if you would use only one core? And for this small one, natrium chloride with 64 atoms, you will need 1 hour. That's okay. The next one, copper silver, with about 200 atoms, it will take 2 days, which is already quite boring. But if you want to simulate something really interesting with thousands of atoms or in several thousand of atoms, it's just not possible. So you really have to use some supercomputer. But another issue is also this calculation is actually the diagonalization of a big, dense Hermitian matrix, right? And you need to store this matrix in your memory. With 2 GB, you can fit on your laptop. With already next test case, you need 72 GB, and you start searching for a supercomputer. So that's the plan of my talk. We will talk a little bit about the hardware and how to program it, just generally. Then I will explain you a bit how the parallelization of FLEUR is done, and I will show you some examples. That's the machine from here, from the Ulish, called Eureka. In the list of the most fast computers in the world, it has rank 52, and its performance is 6.5 petaflops. That means in 1 second, it's able to make 10 to 15 floating point operations. That's a row a bit closer, and one chassis of this machine has 9 nodes. Altogether, this machine has about 2,000 compute nodes. Let's have a look inside a node. This is a node. It has 2 Intel Haswell CPUs, and each CPU has 12 cores. That means that one node has 24 cores. And usually you have 128 GB memory, this node. So for example, our test case from the motivation slide, this copper silver will fit on such one node, but not the bigger one. So usually the compute cluster is quite a heterogeneous system of many different things. As a user, you're usually interested in just usual compute nodes when you can calculate and run your simulations, but there are also login nodes, some spatial nodes for admins, some fancy test systems with some hardware which nobody knows, data storage. But to understand how to program it, we need some level of abstraction, and this is our level of abstraction. So cluster for us is several nodes which are connected through a network, And each node has compute cores which have access to a memory. So already from this picture we see that to compute, code a program, for it we need two different ways of programming. We need something which allows these compute cores to access memory inside a node, but we also need some kind of communication between the nodes. So these cores can access data from this memory, right? So this brings us to two different parallel programming paradigms. Let's start with the shared memory. So in this paradigm, our processors has access to the memory together. So for example, this processor can write the data and the other processor should read the data. Of course, we have to have some way of making sure that we first write and then read, so that we don't read something which is not correct. The dominant standard for this kind of programming is OpenMP, Open Multiprocessing, I guess. So we don't have explicit communication here. We just write data, read data, and we make sure that it happens in the right order. This is an example. I'm not sure you can really see it, but with this kind of programming, we can distribute, for example, some extensive loop. We have a loop where we make calculation on some big array, and we can distribute this work among processors. For this, we add this progress. It can be also ignored if you wish. And this tells the compiler which data we have to replicate, which data are shared, which data are local for each thread, and how this loop is divided between threads. If we have a distributed memory paradigm, then our processors each has its own memory. So these processors cannot just access data from here. This processor have to send data, and this processor have to receive data. So no pragmas anymore. We have to explicitly making receive calls. If your CPU index in this and that, then you receive data. If your CPU index is that on this, then you send data. And this is communication. This is explicit communication. The dominant standard for this is MPI, message passing interface. And this is nice, but sending messages and receiving messages, it's quite an overhead. So you don't not only spend your time calculating some useful stuff, you also communicating with all your processors, and if you have 45,000 of processors in your machine, that can take time. The question is, can I use the message passing strategy inside a node? So if I have such a machine, can I divide this memory between these four processors and not just writing data, but pretend it's separate and send messages? Well, answer is it's doable, but it might be very inefficient. So if you plan to use this hierarchical hardware optimally and get a good performance, you better program your code in a hybrid way. You should use MPI and OpenMP. Let's have a look on the execution model. So with OpenMP, you have a master thread which starts your sequential code, and then it reaches the parallel region, for example, this loop which you have to calculate with several workers. Then this work is distributed between these threads. Then parallel region is over. The worker threads fell asleep. The master thread continues until it reaches the next parallel region. If you combine MPI and OpenMP, then different MPI processors become these master threads, master OpenMP threads, which then spawn each own team of workers. And the communication, actually there are several possibilities how to do communication. There are some possibilities when every thread can communicate with everything. But usually the master threads are communicating outside the parallel OpenMP regions. Now the question, we have our wonderful code which can MPI and can OpenMP, and we have our wonderful hardware. This is the node. You remember with 24 cores. So how do I map it? What's my strategy? One MPI spawn to 24 threads, or 2 MPIs, 4 MPIs, or just forget about OpenMP and start 24 MPIs? Actually, you should test. But usually it's a good idea to use 1 or 2 MPI processes per socket. From the point of view of programmer, you have 24 cores, and the memory address space which is shared between everyone. But in the reality, you have 2 sockets, and this memory is much closer to this processor than, for example, this memory. So it might happen that use explicit communication between them is more efficient than waiting for data as if they are shared. FLEUR. This is the FLEUR algorithm. You probably have seen it already several times. So you start with the initial charge density, then you calculate potential. Then using this potential, you set up Hamiltonian and overlap matrices, and then you solve the generalized eigenvalue problem by diagonalization of these matrices. And then you calculate new charge, and if it's not converged, you repeat this cycle again. These 3 parts of the code scale cubically with system size. So you would expect, if you want to calculate something really big, these 3 parts really matter. And in this blue column, you see how many times it takes usually. It's not always the same distribution. It depends on what you're doing, what the system are, what the properties of the system are. But usually, indeed, matrix setup and diagonalization are the most heavy parts. If you calculate a system with several k points, then you need to set up and diagonalize the matrix for each k point independently, which already gives you an idea how to parallelize this, yeah? Because if you distribute this task between several MPI processes, they don't need to communicate until they are done here, yeah? They need to communicate here. So it should be very efficient. And that is indeed the case in FLEUR. So we have 3 levels of parallelization. The first one is MPI parallelization over k points. The next one, if you have more MPI processes than you have k points, then this matrix setup and diagonalization is also distributed over between several MPI processes. And beneath we have also the multi-threaded parallelization. This picture should convince you that you really have to take advantage from the k-point level parallelization. As I said, now communication should be ideal. This is the speed-up plot. That means we did the same calculation, the same kind of calculation 5 times on 1 node, 2 node, 4, 12, and 36 nodes. It's a bit artificial system with 216 key points. And speed up means that in ideal world we would have the time to execution 2 times faster on 2 nodes, 4 times faster on 4 nodes, and 36 times faster on 36 nodes. And this black one is the ideal scaling. The red one is total. You see, it's not bad, but it's not ideal. But the really, really interesting and heavy and independent part, the setup of the matrix and diagonalization, this blue and green one, it's basically it's even better than ideal. So the point here is, if you have several key points, try to choose number of MPI processes so that they kind of match. Because FLEUR will try to distribute the work in a balanced way. That means if you have 8 key point and 4 MPI processor, then each process will work on key point. So processes are separated. But if you have 8 key points and you will want to start it on, let's say, 7 MPI processors, then all 7 MPI processes will work on each key point together, one after another. And your dream about no communications is forgotten. And it will take much more time. It may be not that painful if your system is small, but it will become painful as system gets bigger. Okay, next level. Actually, it's 2 levels together. The MPI parallelization over eigenvectors and the open MP beneath. This is an X system. That copper silver which fit on 1 node. So our simulation starts with 1 node. It's again the speed up. This one is ideal speed up, and the C wall is not ideal anymore. The red one is again total speed up. Different parts of the code scale differently. We see that on a plot. And from this plot, I would say that for this system, it doesn't make much sense to use 32 or even 16 nodes. Yeah, so this is pretty good scaling. You don't waste too much computer resources. This is la la la. This is the half of the ideal. I wouldn't go there for the production run. And the next reason why we need this level of parallelization, because sometimes our matrix does not fit into the node. We can see how the memory per MPI process goes down when we increase the number of processors. It scales good at the beginning, but then it reaches some value. Yeah, because when you distribute your data between MPI processors, there are some data which you really distribute, like this matrix, but you also need some data which, some information which every MPI processor should know. And there is some amount of it. And if your system big, then this plateau will get higher. This is the reason why it's not a good idea to use only MPI parallelization if you calculate something big. The FLEUR is part of the MAX project. MAX means material designs at the exascale. Reaching the exascale is quite a challenge from technological point of view, but also from the software point of view. The current fastest computer in the world has 200 petaflops. So basically, take 5 of it until you reach exa. And there are announcements that in the USR they go in to build 2 exascale machines by the end of 21, and there are also some plans in Europe to build an exascale system to 22 and 23. And since FLEUR is part of this project, so we are also making FLEUR able to be run on this kind of machine efficiently. So what's FLEUR performance? This is again the scaling plots, but a bit different. It's not speed up anymore. So now the lower is the better. It's the execution time. We have 3 systems here. This one, already well-known copper silver, from 1 node to the 16, and these 2 bigger systems, one with 500 atoms and one with over 1,000. You see, the bigger system cannot fit in so less nodes, that this one starts at 8 and this one starts at 16s, but it scales further. But we also see that it doesn't scale forever, right? So if you are thinking how wide I can spread my system over the cluster, can I use the whole cluster for my nice system with 20 atoms? Probably that's not a good idea. So don't use more than, I don't know, 16 times more nodes than you fit minimally. This simulation were done with the previous FLEUR version, the release 3 from the last year. It was nice, but we made it better. This is the comparison between the last and the very last, no, the previous and the last version. The release 3, this green one, and the release 3.1 from like last week. We see that it's not only quite faster, but also scaled just a little bit better. And with this version, it was possible to simulate system with 2,000 of atoms. The reason why it's so much better, it's because Daniel implemented new data storage, and the problem with modern supercomputers is that you have very nice processors which can do lots and lots of flops, but the memory is so far away that the data just didn't arrive fast enough. So your CPUs are starving, and the optimization is basically how to use and reuse data and how to deliver it fast enough to the CPU. This is another nice calculation. Now with more than 3,000 atoms, to do this calculation for one iteration with one key point, it took 3 hours on the 500 nodes. And basically, for this system, you need more key points, but this is ongoing. So when you use FLEUR, when you start your simulation on a supercomputer, you want to make a decision: how many nodes do I need? How many MPI processes do I start? And how many threads? Right. So if you're choosing the number of nodes, it basically depends on how much memory do you have on the node, and then you might want to scale it a bit further, but don't do it too much. Then when you choose number of MPI processors, think about key points, so they match. And when you use multi-threading, use all cores on your node. Usually it's a good idea to use 1 to 2 MPI processors per socket, And don't use full hyperthreading. For this kind of codes, it's usually not. Hyperthreading is starting several threads on one core. When you work on such a machine, you usually send your job in a queue. For this, you need a batch file. This is the example of a batch file. So you say, I want to make this calculation on 128 nodes. I want to start 4 MPIs per node. I want to use 12 cores per every MPI process. This simulation will be killed after 7 hours. Yes, and I want to use the node exclusive because in some supercomputers are allowed to put several jobs from different people on the same node. So you usually don't want that. Then you might want to extend the software which you have. I'm using also the ELPA library for the diagonalization, which I compiled myself. That's why I need to provide the address for that. I need to provide OpenMP with information how many threads should it start. Well, and then I run the calculation. It somehow took much less time than I expected. So basically, that's it. That's what I have told you. The level of understanding what cluster is at least you should understand that it has many nodes, and each node has many cores with memory inside the node, and you should communicate with this memory somehow. To program these systems, you need both shared memory parallelism and distributed memory parallelism. And in FLEUR, we have 3 levels of parallelization which you need to take into account. And well, if you do it correctly, then you can simulate very nice systems. Thank you.